Hello everyone. So we will start shortly. I'll just wait for a couple of more minutes to 2 more minutes to see if more people join. Then we will get started. Can can any one of you confirm by writing on the chat window whether you can hear me or not, and whether my screen is visible or not? Okay, thank you so much. Yeah, just 1 more minute and then we will get started. Thanks. Okay. Okay, so let's get started. Hello everyone. Welcome to workshop on secure computer systems. Today's session is was actually optional. So I think because of that many people have not joined, as I recommended to join only if you are new to computer science. And about me, I am Nikita Yadav. I'm a PhD student in the Department of Computer Science and Automation in IISc Bangalore. And so this workshop is regarding security, and the today's agenda is it's a primer. So we will be discussing very basic concepts related to how programs are turned into processes which run with the help of the operating systems, and we will look at the components of the computer systems. Then day 1, 2, 3, they will be completely dedicated to security concepts, and then these day are full day workshop and includes demos, quizzes, and Q&A sessions as well, along with the normal lectures or class material. Then the day 4, I have kept a 4-hour session which is open, and if you have further questions, if you have, let's say you try the demos, or if you get any doubts after the 3 days of the workshop and you want to ask something, or if you want to do more quiz or something, then you can join for the day 4 as well. Although I understand that is also a working day, so it's may not be possible for everyone to join. Regarding the schedule of each day, you can visit the website, which is shown here, and I have already sent you the link to the website. When you go to the schedule tab, then you can see there the schedule day wise, what topics I plan to cover. There, I may need to modify the schedule a little bit depending on what I may be teaching that day, although it's more or less fixed, but it might change a little bit here and there. Just one, before I keep going on, just I want to say one thing, that I have uh, made a setting on this in this meeting, that nobody can unmute themselves or turn on their camera, so that the everything goes on smoothly. But if you want to speak, then you can raise your hand and I'll be able to unmute you. And if you have any question at any time, you can leave them in the chat box, and I will look at the chat window from time to time and try to answer your questions. And yeah, so I've already introduced myself. I'm a PhD student, fourth year PhD student in CSA department in Indian Institute of Science, Bangalore. I am a member of the Computer System Security Lab, which is led by Professor Vinod Ganpati. And although my broad area of research is system security, I'm currently focusing on attestation techniques, particularly control flow attestation. And you can visit my website to know a bit more about, if you're interested in my, to know what I am working on, what I have done before, my research papers, etc. Then you can visit my website and take a look. So the goal of this workshop is actually to just an introduction to system security, because system security is actually a very broad area, and it is so broad because of the domains. So if you are applying security techniques to web systems or like websites, or whether you're applying it to say satellites, or you're applying it to embedded devices or networks. So because you can apply security, you need security in every domain. That's why security, and there are variety of attacks and defenses that are needed. So computer security is a very broad area, and usually it is not a course which is taught using any textbooks, because it is a area which keeps evolving as new attacks and defenses emerge. So that is why the courses are usually research paper oriented. In this, while we look at the class material, I will discuss the attacks, defenses, and everything. But if you're interested and if you want to read the papers from which the lecture material has been made, then you can refer to the papers later. And just that in this workshop, it is impossible for me to cover the breadth of the security, system security area. As I said, it's very broad. So we will focus only on some topics which are related to memory vulnerabilities, which exist in the programs that can be exploited by the attackers, and to say crash the program or run some other malicious operation or something. And then we will look at that how we can defend against these memory attacks and vulnerabilities. And after that we will have so these first 2 days, day 1 and day 2, are dedicated to these memory vulnerabilities, defenses, and demos related to those. And the last day is for some advanced topics, which is trusted execution environments. Particularly we will look at the ARM trust zone, which is widely deployed in ARM hardware, and it's a trusted hardware. So we will look at that. And then also one of the very important techniques in security and also otherwise is virtualization. So we will look at the virtualization. I'm sure most of you would be well uh, aware or well familiar with virtual machines. And so instead of virtual machines, we will be looking at containers in more details. They're also very popular nowadays, and due to emerging microservices and everything. And so we will look at containers and how we can create and use containers. And so for that, we will look at the Docker containers. And just a clarification that this workshop is not related to cryptography or privacy. It's actually systems security. So it is not cryptography. And the target audience for this workshop is anyone who is new to computer system security, or who has even some background and want to learn more. You're very well welcome to attend it. And then for today's session, anyone who is new to computer systems and would want to just have, say, review the topics, just look at it. So that's the target audience. And before I start with the material for today's talk, I would, wa- I wa- I'm want to thank and I want to acknowledge that the content of this workshop is adapted from the security courses which are offered by Professor Vinod Ganpati in IISc Bangalore and Professor Chester Ribeiro from IIT Madras. And with that, I will get started. But before that, if any one of you have any questions, then I'll just check the chat window. Okay. If you have any questions, then you can post. Otherwise, let's get started. Okay. So a computer system. So computer systems consist of these different layers. So you can think of the computer system as different layers. So it is composed of these layers. So starting from the hardware. So what is visible to you is there is a monitor, there is a CPU, there is a monitor, there is the CPU that you can see, keyboard, mouse, and everything. So these are the hardware which are on more, say, fine grained granularity, they will be composed of, say, transistors, capacitor, etc. And these hardware components then come together with the help of the software layer, and then they work together. Okay, so the hardware and so here I have separated the hardware and the processor. Hardware in general refers to the other hardware components like your keyboard, mouse, monitor, printer, etc. And the processor is your central processing unit, the processor, which is going to run your program, which is going to run the softwares. And then your applications. So for example, this Teams or Office or Chrome, etc. These applications that you use on day-to-day basis, those applications are here. And the now how do these application gets run on your computer system, on your hardware? That is enabled by this layer, which is called the operating systems. So this is like an interface. It is a software layer which is sitting between the applications and the processor, and uh, it provides this, it enables the applications to run on the processor smoothly. So it manages the applications as well as the hardware. So this is the basically the manager of the other components. Now, first of all, we will look at the application and then the operating system and the processor. So first we are going to look at that how do you say, how does your program gets turned into a process? Okay, so let's consider this very simple example program. Let's say that this is hello.c program, okay, which nothing but it just print, there is only one printf statement here in the main function, which is printing the string hello world, and it will be printed on your terminal. Okay, now to now first of all, to run this program, you have to give this program to the compiler. And what does compiler do? A compiler is another software which takes your program and then it converts it into machine code, which can be run on the processor. So it is the translator which is translating your high level code, which is written in these languages, high level languages like C, C++, Java, etc. It takes that code and then it translates it into low level machine code, which can be run directly on the hardware or the processor, because the processor doesn't understands only machine level code. Okay, we will also look at this machine code later in the demo. And so for this is very important that we have this software layer. We have this software, not the layer, software, which is called a compiler. Here we are using GCC compiler. Okay, it's a C compiler. Okay, so it converts, so it takes the C program, and then this command, particularly gcc hello.c, is going to take your program hello.c, and it is going to generate a object file. Now what is the object file? So object file is like just another format. It's basically a file which, so first of all, you're going to take your program and your GCC compiler is going to generate these object files, and these object files are then linked together by the linker to generate the executable. Okay, so the object file, basically the compiler is generating this object file, so it is actually creating like sections in like code sections or data section, etc. So this file is stored on the disk, and this file is stored in a particular format, and that format is called the ELF format, executable linking format. Okay, so this particular file is stored in this particular format, ELF format, and then if you want to run this file, then you can give this command. Sorry, this is an executable file, not an object file. And if you want to run this command, then you can run this executable file, then you can give this command /a.out. So when you give this command, then this executable file, which is stored on the disk, will be brought to your memory, that is RAM. Okay, and then from the RAM, it is then read by the processor. The instructions are read by the processor, and the processor will execute the instructions. And When your and in this state, when your program is executing, it is called to be a process. So a process is nothing but a program in execution. So when you take the executable and then you run it, then you generate a process. Okay, so currently this Teams is actually a process. And so here, just to reiterate, you take your program written in C, you will write it, you compile it with the compiler GCC. With this command here, I would like to correct, with this command here, you are generating an executable, not object file. It's an executable file, a.out, and then you, to run this a.out, you give this command /a.out, and then a process is generated. This file will, basically the code in this file will execute, and the hello world string will be printed on your terminal. So this is how your program is converted to a process. And so now closely looking at the ELF format, which is the executable and linkable format. So the ELF format is a standard file format which is used for executables, object code, shared libraries, and code file, etc. So the executable format has two different views, or two different formats. Like, one is called the linking view, which is for the object files, and another is the execution view, which is for the executables. So now, and in this executable format, the first thing we have is the ELF header. So the ELF header is basically, it's the description of the file organization, like the how your file is organized. And then after that, you have a program header table, which is optional in linking view. Then you have sections, different sections like code, data, etc. And then finally, you have a section header table, which basically is contains the information like where each section is located. And now let's look, and on the, in contrast, in the execution view, you have the ELF header and program header table, but and segments. You do not have section header table here, or it's optional. Okay, so in contrast, you have a program header table and the segments. So now looking at it one by one, so in the linking view, you have first the ELF header. The ELF header, it's like information. It's the file information, and it contains the type of the file, like what type the file is, the for what architecture this file has been generated, like whether it is a Intel architecture, ARM architecture, etc. What is the entry point of this file, from where this file will be started, and the program headers table offset, or number of program headers, or number of segments, or number of sections, etc. So it contains information about the file organization, like how the file actually looks like. Then the program header table, here it's optional, but it describes the information about the segments or the program regions, like what is the type of that segment, what is the size of that segment, what is the virtual memory address from where the segment will be starting, etc. And then these sections are, they contain the various types of data and metadata, such as there can be a section for code, another section for data, another section for symbol table, relocation information, etc. So there'll be different sections. Your program basically, which you have wrote, will be then decomposed and stored into different sections. Like your code will be stored in the code section, your data such as global variables or something, they'll be stored in the data section. Then your compiler will also generate a symbol table, which will be contained in the symbol table section. And since your program can, at runtime, the different sections can be, or the different segments can be relocated, like they can be placed at different at virtual addresses. So there'll be relocation information, and like which variables, or like which symbols are reallocated. Then The section header table, it stores the metadata about each section. Let's say the code section. So it will contain that, okay, this is the section one, the name of the section, the type of the section, and then the sizes, the flags, offsets, etc. Similarly, in the executable view also, we will, particularly here, since most of these things are similar, only what is differentiating is the segments. Here, instead of sections, we have segments. So what are segments? Segments are nothing but you combine different sections together to create segments. Okay, and each segment in the ELF, so will have a different, like you, when you look at the segment information, you can find the type of the segment, which will specify its purpose, such as whether it's a loading executable code or is it like initializing data, etc. Then the attributes or the flags of that segments, like the permission of that segment, whether it is a readable, writable, or executable segments, etc. Then content of that segment, like what is the content? Is it the code? Is it data? Or does it contain symbol table, etc.? And finally, your memory mapping, like at the program load time in the in your segments, you will also specify that what is the virtual memory range of this segment, or in your program header table, it will specify that what is the starting virtual address of this and what is the starting physical address. So these memory mapping information is also present, which will be used by the loader at when the program is loaded for execution. Now we will look at these things, like process. First, we will take a program and compile it and look at the binary. Then we will look at the ELF format, and then we will look at the machine instruction by disassembling the program binary. So for that, but one second. Okay, I hope it is visible, and I will check if there are any questions. Okay, so here we will, okay, so here we have this program, the simplest, the simple program that we just saw. So we have this program, which is here first we have this character string, okay, str, which is set to hello world, and then we are giving the starting address of the string uh, to printf to print it, and we are passing percentage s. So it will, here this will be the address, starting address of the string, and it will print hello world on the terminal. So and let's just compile this. So when we use the this command gcc hello.c, then we generate this file. Okay, let us look at the file. So this file is has these permissions. These are for like user, others, root user and others. So this file has here permissions read, write, execute. So that means the file can be executed. Okay, so it's an executable, it has the execute permission, and then we can execute this by using the command /a.out. And when we run this, then we get this output, hello world. So now we are going to look at first the elf header. We are going to read the elf header that we just saw. So for that, we are going to use this command, read elf -h hello world. Okay, and here I have a.out is also okay. Okay, so then we use the to read the elf header, to read basically the elf format of the binary. We can use this read elf tool, and here by giving the option -h, by giving option -h, we will read only the elf header. This elf header first contains also all the elf files. They start with this magic number, this value, and this is for identification purpose that this file is a elf file. Okay, and this value, this byte sequence basically is ASCII for elf, ELF. And then we have in the elf header some other informations about the file, such as the OS, for which it is compiled, Unix. Okay, for the machine for which it is compiled and it can be run on, so it has AMD or x86 Intel processor. So this file is compiled, basically this binary is compiled for AMD or x86 64 machine, so it can run only on AMD or Intel machines which are configured with 64-bit. And then there are some other informations also, like the entry point address, which is here, and the start of the program header. So the program header is 64 bytes into the file. So this is the offset of the program header. And this is for the section header, it is 6504 bytes into the file. And then we have also information like number of section headers is 29, number of program headers is 9. Okay, so this is the elf header, and next we can look at each section, like we can look at the sections in this file. So this file has 29 so there are 29 section headers, and in this section header here we will we have information like the type of the section. Okay, so the type of the section here, like this is an object type. So as you can see, these are the names of the different sections like libc, csu. Okay, then we have here information like the type of the section, the information, the bind with, and this is the symbol table. Okay, so like the different functions which are being used actually in this program, like printf, so that information is available in the symbol table. Now, after that, we can I would like to see if it's different. Yeah. So to read information about the different header, like this different sections, so we can use this read elf minus capital S here. Then here you will have the name of the section, the type of the section, the address, offset, size, flags, etc. information. Uh, like this is the name of the section. The prog bits means that this section is actually for the program that you have written. So your program is stored here. This is the starting virtual address of this program, and then the address, and then the offset. Then this uh, the values are a bit difficult to read like this, and then yeah, one, two, so the sections which are actually marked, so these are the flags like AX, WA. So these are the flags. The flag is basically gives the information like what are the permissions of this section, whether it is executable, readable, writable, etc. So the sections which are marked with X, only those sections are like the text section. Actually, this section contains your program, and this section type is prog bits. Its name is dot text section, and this flag is AX. So that means it's an executable section. Okay. And then the sections which are marked with W, those are writable sections. Like this is your dot data section, which contains your data, and the dot BSS also contains the data. So these are the different sections. So you can get information about different, like you can see how many sections are there, what are the different sections, and what are the permissions of each section. To inspect that, you can look at the read else minus S and the binary. You can check that information here. Now, after that, you can also read the program header information. So for that, you have to use read elf minus H. So this is your program here, as is the entry point is 0x5A0, and so it will be started from this address, and there are 9 program headers here, like, and this is the type of the header, like the type of the header, whether it is a loadable, executable, or whether it's a stack, or it's a relocatable, relocation information, etc. So this is the type of the program. Sorry, this is the type, okay, of your segments. So the program headers contain information about the segments. So here there are 9 program headers, and then this is the offset, like from where in your elf file this uh, particular segment is located. That information is there. It is located at this address. Then in your program header, it is also specified that where this uh, segment can be located in the virtual address space of the process. So this is also specified here, and then physical address here specifies the location in the physical address where your segment will be located. Although this is mostly ignored, because the loader will decide where it is. Sorry, this is not the loader, this is decided by the memory management unit, which will allocate physical pages for the virtual pages. Then you have the file size, this is the size and the memory size, and after that you have here the flag, the permissions on these segments: readable, writable, executable. So here E is the executable, it is the loadable executable segment is this. So this one is the one which is containing your code. Okay, and the segments are composed of different sections. So different sections are combined together to form the segments. So here you can see that information, like the first segment contains of only this um, section, and like 03 segment consists of all of these different segments, sorry, sections. 03 segment contains all of these different sections. So here we have seen, so what we are seeing is that when you generate a binary, when your compiler is generating a binary, then how that binary is actually stored in your system, in your on the disk. So it is stored in using this ELF format, where we looked at the ELF header. We saw that the execute linkable, we saw that it has two different formats, one for object files, which is a linking format, one for the executable files called an executable view. And we saw that your program is stored into different segments. So your program will be mapped into different segments, and then these different segments will have different permissions. Some of them are executable, some of them are only writable, like the data segment. And then this information will be used by the processor to run when it has to execute this program, like where to start this information. It will read from the ELF format. And so next we can look at the, so this we have seen how the file is organized, how the file is stored on the disk. Now let's look at inside the executable file, which is generated by the compiler. So here we can use this tool obj dump. So this will disassemble with this flag disassemble. And then when you pass, you can first is you will use this command obj dump minus minus disassemble minus all, and then you give the name of the binary, and then you can redirect the output if to some other file. Okay, this is redirection. And then let's look at this file. We will open this file here. And so this file, as we had discussed before, it is the ELF format 64x86. It has the disassembly of different sections, which we have looked here. And then now let's look at your main function. Yeah, so the main function is here. So this is the main function that we have written. So our main function actually consisted of first creating a string and then passing that string to the printf function to print it on the terminal. So here you have the call to printf function. Okay, this is the call to printf library function. And so these are, on this side, these will be the virtual addresses, and on these are the push, this percentage RBP, and so on. These are the assembly instructions. Okay, and what is these assembly instructions are converted? They are actually stored in this form, basically as these bytes. So here, this the middle values, these are actually your machine code. So this is your machine code. So value 55 here, when your processor sees this value 55, this will so the processor will basically, when it executes, then it will perform the operation, this push uh, percentage RBP. So it will push the content of RBP register on the stack. Okay, so this is the assembly instruction, which is close to the architecture, the ISA, but it is still understandable by us humans, and this is the machine code which is understandable by the processor, which the processor reads and executes. So okay. Yeah, and so when you create these when you are going to run your program, then it is going to create a process, and you can list the processes which are running in your system by using the ps command in Linux. So you can use different flags with it, and then you can pass the output of the ps command. You can use the pipes, and you can the grep, basically grep command lets you find some pattern. So so you can give here the say the pattern hello world, so the output which is generated, because if I run ps command currently, so there are so many processes which are running on my system, and it will be hard to find out the hello world say process. So you can basically search for the your particular file that you're looking for by using the grep command. And so then the processes, they have a virtual address space. I'll come to the address space probably later, but every process has its own virtual address space, and you can look at a process virtual address space, a virtual memory map, by using for that you can go to this directory slash proc slash the PID of the process that you are looking for, and then slash maps. Okay, and for this you need the sudo permission, and then you can actually look at the memory map of the like the virtual memory map, so different virtual VMA areas and etc, the permissions and flags etc for those VMAs. So this you can do for the files which are running, and you can list the processes. So sorry, the processes which are running, and you can list the processes by using the ps command. So like not for actually the hello world, but in general, if you will see like here we are running these so these are the processes which are currently running on my system. So here these are probably all the chrome tabs which are open, and here um, maybe it's also like I can also mention that each tab in your browser actually runs as a different process, because when they are run as different processes, then they have a different virtual address space. That means they're isolated from each other, so which provides more security. So here each chrome tab is running as a different process, and these are the different processes which are running on the system. And if we have to pick up, let's say, this particular PID, we can take this, we can look at the maps. So this is the memory map of this process. Okay, so you can see so many, because this process is of course like this is a chrome process. This has huge data, like huge code probably. So there are lot of file, that a lot of libraries which are let's say loaded here. Okay, and so you can see, so this is the so this will be the virtual address range where this particular section is loaded. This is going to be the permission, the flags, etc, and these are the device information, like from where this is located, etc. So this is how you can create a, you can take a program, you can compile it, you can create a process, then you can check if the process status, like you can check, you can list the processes which are running on your system, and then you can also inspect the memory map, virtual memory map of that process by using these commands. So these, and you can look at the elf header to get information, like the looking at the elf header basically will just give you information like for which processor this binary is has been compiled for, or such information you can get from the elf header. So with this, I will stop for some time and look at if anyone has any question, then I can take that. And otherwise, we will move on to the next. Does anyone have any question regarding what we have discussed so far? Is it clear? Okay, maybe we can have even a quick feedback on to whether you found it useful or not uh, at all, or you were already familiar with everything. Yes, I will be sharing all of these things after the session and you can try them done. I've actually created a Teams which I should share now. I forgot to share in the beginning. So I have created a Teams. I will share it tomorrow also. But I can share it now. No, sorry, yeah. You can try and join these things. Uh, and you can also tell me if you're able to join it. And then I will put these program examples and commands, etc. The demos and information here on the piece in the file segment section. You can find that. Okay, so then since we have already currently only looked at the very basic C program, compiling it and all, so maybe we can have do a quiz on programming in C. It has very basic 10, 12 questions, and I will share my screen here, and I have the questions. Yeah. Mm, wait a second. I wanted to get. Yeah. Yeah. So the first problem here is in C programs when we define a function. So which of these statements is true for a function? So a function is, first option is a block of statements to perform some specific task. Second is it is a fundamental modular unit to perform some task. Third is it has a name and it can be used multiple times. And the last option is all of above. So like main is a function and which is basically the entry point in the program. But apart from main, we can define functions in our program, and then we can call those functions. So please, you can write your actually you can write your answers in the chat box. B, D. I should actually show you the. How is it possible for me to see the chat simultaneously? Let me see if I can create a Q&A. Okay, so I will post it here so that you can see it. If you and you can add your answers here next time. Now it's okay if I did already do the chat. All the yeah, B is also there. And okay, yeah, so most of you have answered it correctly. The correct answer is option D, all of above. So basically, statement A and B are actually same only. They're just worded differently. So it's a block of statements, which is true. And most of the time, although it's not a necessity, but the idea of a function, what is the idea why the function exists is like when you're creating these functions, then you call a function only for a specific task. Let's say copy. So you want to copy your content from one buffer to the other, or you might create one function to say sort the numbers, etc. So these functions are usually created to perform specific tasks, and they're modular because then you do your whole program is not written entirely in your main function. You have these different functions and you can reuse them multiple times. So that's why it is modular, and it has of course a name and it can be used multiple times. So all of above are correct. So if you have any other answer, and if you have any queries regarding that, then please feel free to discuss that in the chat box. Now for the next question, it got hanged. Yeah. Okay, I will add this to the Q&A, and then because it will be better. Okay. Yes, so what is the output of this program? You can hopefully see it in your teams also. If not, just let me know in the chat box whether you can see these questions in the Q&A tab. If not, just let me know in the chat. Otherwise, we can. So this is the program. Okay, it has only one function main. It has two integers, x and y. X is equal to 1, y is equal to 3. Here, first you have created one more integer, and you're doing something, and then you're printing the value of x and y. So here you have to tell what is the output of this program. 3 and 1. 3, 1. Yes. So yeah, so that is right answer. So here you are actually swapping the values as you correctly said. So you were first storing the value of x in t variable, and you have already stored the value of x in t. So now you can change the value of x to y, and finally you will uh, save the value from, you will like store the value from t to y. So in that way you have swapped the values here. Okay, so that was easy. This is, of course, I don't think I would need to copy. The loop which is executed at least once is. So you have these three options. and of course none of the above also. So which of these loops will be executed at least once, irrespective of the condition of the loop? While loop, do while loop, for loop. Yeah, so the answer is correct. It's do while, and we, yeah, that is right. So then I think I can't share it there because it's a picture. So I was, let's look at it here only. What is the output of the following C code? So you have this code, and you have to tell me which print statement will be printed. What will be printed? You can write your answers here, and we have the code here. Okay, I got one answer, true. Any other answers? Okay, I don't know if I can see Q and A's in here. So let's see. There are three commands here. True, false, false, true, false. Okay, so yeah. So true, false, both will be printed here. And let's look at that. I'll just explain why is it that. Why is it so? Okay, so first here you have variable a initialized to value 1. Then you have the if condition where you are doing a minus minus. I hope that you understood because the quality of is a little bad, but it's a minus minus. So it is a post decrement. Okay. So in post decrement, what will happen is that to evaluate the condition, that whether the condition is true or false, first, you are going to use the original value of the A. The original value of A here is 1. So the condition will become true. But the value will be then decremented to 0. So the value will then become 0. So since the condition is true, it will be printed. True will be printed. Now your A is 0. A is equal to 0. Now you come to the second if condition. Here the it is a pre increment. So here A is equal to 0, but before the condition is evaluated, it will be incremented by 1. So your value 0 will become 1, and then the 1 value is your condition, which is true. So then it will print false. So here both of the print statements will execute, and your output will be true, false. Now the next, I hope that was clear. If not, you can ask me to repeat by writing in the chat box and the problem number. And the next question is, which of the following statements is or are false? The first statement is array elements are stored in memory in contiguous locations. And second is an integer array always terminates with a null. Now, B. So for this array, okay, can you answer in the Q&A tab? Which of these statements is are false? You don't have to tell the true one. The which is false. B is false. Okay. Mm, yeah, that is correct. B is false, but there is only one answer. I hope everybody is familiar with arrays. So, array is just a data structure. So you can create array by the syntax like int a is the name of the array and then two square parentheses, and then in that inside the square parentheses you can specify the number of elements like 5 elements. So if you specify 5, then an array will be created of 5 elements where each element is an integer. And when this so the way this array is stored in your program memory is in contiguous locations. So if your array element first is starting at address say 100, then the second element will start at address 104, considering that each element is of 4 bytes. Okay, and then the next will be 108 and so on. So array elements are stored in memory in contiguous locations. An array is just a structure to store the data. Okay, it's a data structure, and other structures are like queues or linked lists, etc. And an integer array will is not terminated with a null. So it's true for strings. Strings are non-terminated, but an integer array is not null terminated. So only option 1 is correct and the option 2 is incorrect. So the answer here is B. Now moving on, the next question is what will be printed after execution of the following code. So it is again related to the array. As I was just saying, here A is the array name, and you can read it like A is a array of size 20, like is of not size. Basically, A is an array of 20 elements where each element is an integer. Okay, and then you can initialize this array using this syntax. Like you can use these curly braces and then you can specify the elements here separated by commas, and you don't have to write here 20 elements. You have written here only 6 elements. So that's okay. The first six locations in the array will be filled with these values. The rest locations are garbage values. Okay, but they are allocated here because you have specified 20. But now the question is actually related to the print statement, that what will be printed here when you say printf %d, comma 3, then parenthesis a. So what will be printed here? Okay, so next array prints %d, comma 3a. I'm just writing very roughly, and you can add your answers here. And I'll just open the window here so that you can look at the entire code. Okay, there is one comment. I encourage everyone to try. It doesn't matter if you get it wrong. So if you are unsure, then still you can write your answers. Okay. So here the answer is 40. And why is it so? Because so when you use a without any, so first of all, this 3 parenthesis a, this will actually, you can rewrite it as a plus 3. So this parenthesis operation, when you write, in general, you what how do you address the elements, how do you index into the array? To index into the array, the general syntax is a of, first you write a, then parenthesis, and then the index, like a0, a parenthesis 0, a parenthesis 1, etc. We have just reversed it, but that didn't that is exactly same, it works exactly same, because when you write a parenthesis 3, that would mean a plus 3, and here 3 is actually the increment in the addresses, like you have to do increment the address 3 times. Okay, so initially your a is here the address of the array, the starting, the address of the array, or the address of the first element, okay, which is same. So it is pointing here to element 10. Okay, then when you say a plus 1, it will point to 20. When you say a plus 2, it will point to 30. When you say a plus 3, it will point to 40. So that's why here it was going to print this value. So that is why it is going to print here 40, because your address, starting address of the array is incremented by 3. So here 3 actually is not like 100 plus 3 is 103. Here 3 increments will be in the size of the like, what is the size of the integer. So if the integer is 4 bytes, then it will be 3 times 4. Okay, that will be the increment. So now let's look at the next problem, which is what will be the output of the program here. Now here you have a character string. Okay, you have a character array. Basically, it is also, str is an array where each element is a character, and you have initialized it like this. Okay, and then you are using printf, passing percentage s and then str. Writing string. You can write your options. Yeah, so that is right. So it will, so if you will see at the string, so here actually you have this backslash zero, which is actually the null character. So, and the strings are null terminated. So when you're using this percentage s, the printf is going to start printing from this address, which is specified by str, the starting address of this array, but it will stop as soon as it sees a null character. So this is also null terminated. The entire string is null terminated. After string also there is a null character, but a null character already exists between array and string. So that's why it will stop right here and will print only till array. So it is option A is correct. Now only a few more problems. So the next problem is it's related to for loop, and here you have integer n, and you are setting n is equal to 10, checking the value of n is less than 10, then decremented in it on every iteration by 1, and then you are printing the value of n. So what will be the output of this program? Sorry, I think there is a correction. N is less than 10. Oh, yeah, n is less than 10. So what will be the output of this program? Okay, yeah. So there are two answers, and so here there are two possibilities which have been answered. Okay, so the first answer is no output, and the second one is infinite loop. So the infinite loop, why is it possible? Because you're starting from 10 and then you're decrementing it in every iteration, and then you're checking it whether it is less than 10. So if it is decrementing, then of course it will be less than 10. And so that's why infinite loop is possible. But that is actually not a correct answer here. And the reason is because when you are going to start the for loop, first n is initialized to 10. And even before you enter the for loop, you're going to check for this condition. So the condition is checked here before even entering the for loop. Okay, so n is equal to 10, then you have to check n is less than 10. 10 is not less than 10, so this will fail, and that's why you will not enter the for loop, and so there will be no output to this program. So I hope that is clear. And so then moving on, we have this next question: which of the following is not an infinite loop? I think it's an easy question. uh, I will just write here not infinite. You can add, you can then add your answer options here. D, right. So all of them are right answers because all of the first three syntaxes, they are actually infinite. The first one, there is no condition at all, so that's why it's infinite. The second one is infinite because here you are not changing the value of x. So x was initially 0. It is checked with value 10, whether it is less than 10 or not. And then you're not changing it, like incrementing it. So that's why it will always hold true. Here the assumption is that x is also not being changed in the body of the for loop. And then C option is while 1. So 1 is always true, so it will be an infinite loop. And the last one is while 0. So 0 is false, so it will not be an infinite loop. And then the next one here is, can I copy this as well? Let's see. No. Anyway, so this is an interesting question. So I'll just first write here print value of m and n. So you have to tell the value of print, what will be the value of m and n. And this is also the last question for the programming in C quiz. So this is, you have to here tell what will be the printed by this printf uh, like printf command here, printf statement. Basically here initially you have two integers m and n set to value 0. Then you have this while loop where you are checking m is less than n comma n is less than 7, and then in the inside you are incrementing the value of m and n. Okay, so can you please check your answer again, because we are printing only two integers here, so only the value of m and n. So if you can recheck your answer. Okay, so then there are four comments. Okay, okay, so 55444677. Okay, so we have a variety of answers here, and so the correct answer is 777, and why is it so is because so we are going to start from with value 0 for both the variables, and then of course these two, both of them will hold true, both the conditions will be true, and then we increment the value, and then we again recheck the condition. Now the catch here is this, that the catch here is actually, the first catch here is that when you are going to check, so when this comma, because of this comma here, comma separated conditions, when you're going to check, first you're going to check for m, whether the condition hold true or false. You're going to check it, but then you check for n. So if basically whatever the outcome come for m, you discard it. It's not even used. It's not like an and operator or operator. It's actually not used at all. So whatever the comparison of n value with 7 generates, whether it is true or false, only that will be the output of the condition check. Okay, so that's because of this comma operator here. That's how it is going to work. Now, with that information, I mean, basically, we don't even need to check whether m is less than 5 or not. Now, for n is initially 0, 0 is less than 7, holds true. So then we increment the value of both the variables, they become 1, then we go back. So we will do this until, let's say, n is 6 and m is also 6. So 6 is less than 7, so we will enter the loop, right? Both variables are now 6, we enter the loop and both are incremented and then they become 7. So we'll come here, 7 is less than 5 is false for m. 7 is less than 7 is false for n. Now we break out of the while loop only because the condition is not holding for the second here, for n is less than 7. So that's when we come out, and that's when both the variables get the value 7. So that's why 7 comma 7 is printed here. Now, okay. Um, so that's, we have done only few questions with programming in C, and they are just only to, they were just like a quiz, uh, but nothing like an prerequisite or anything. Okay, so even if you didn't get answers to some of the questions correct, it is okay, it doesn't matter. But so next, we're going to look at the, we're going to continue with the next part of the slides. Um, so I will continue with the next part of the slides, or we can take a quick break if you want. If you want, then we can take a 5-10 minutes of break and then restart with the next part of the slides, because continuously it can become boring or difficult. So you can let me know if you want a break. Otherwise, I will just continue. Okay, so then, okay, continuing. So next we will look at operating systems. Okay, and just some basic concepts of operating systems, and nothing in depth actually. So for this, I have side credits to Professor Chester Rivero from IIT Madras. And so first, what is OS used for? So what is the purpose of OS? Okay, so the OS, there are these two main purpose of OS. Of course, there are others, but there are the two main purpose of OS. The first one is hardware abstraction. So what does hardware abstraction means is that your computer system has many hardwares like printer, or say a keyboard or a mouse, a monitor, etc. Now, when your program wants to use these hardware, let's say your program is using this printf function. Okay, you want to print your output on the terminal, but you are not giving any information like how the printf, like you are not telling where it should be printed, whether it is on a terminal, what should be the location, what will be the color, what is the font, how will you interact with the monitor hardware, etc. So you don't have to worry about all of these details. And the OS is the software layer which is handling all of these, which is abstracting away these details from the application programmers, and thereby allowing the application programmers to write, like make it easy for them to write the codes and to use the hardware which is present on the system. So the next one is resource management. Of course, for example, your machine, it has like only one monitor, right? And then there are multiple applications which are running. So which of the application is going to use the monitor, or which of the application is going to use the processor to run, to execute, that is managed, because the resources are limited, and there can be multiple applications or which want to use these resources. So the OS is the entity which is maintaining these resources, assigning these resources to the processes, so that the processes, for fair allocation, so that not only just one process is all the time using the processor, there is fairness, and then it's again like easier for the programmers. So it manages the system's resources. Now, sharing the CPU, so as I said that there are multiple applications which can be running, and assuming, let's say you have only one processor, it's a uniprocessor system, and so all of these applications will have to be run on the same processor, but there is only one processor. So who is going to use the CPU? So for that, what the OS basically decides that at what time which application is going to be allocated CPU time. Okay, so like here, this can be one of the examples. Like first, the CPU, first the OS can decide to give let the application one run on the processor. Okay, whenever the application one finishes its execution, when the application one program has run completely, then it will be free, and then it can allocate application 2 on the processor. Okay, then application 2 will also run till its termination, and then application 3 is allotted, and after that application 4. So, so this is one of the ways in which the applications can be run on the scheduled basically onto the processor. So the OS is managing the scheduling of the processes. Now here there is a problem, like when your application is running, and let's say in your application you need input from some other device, let's say you need from the keyboard, or you're waiting for some network packet or something. At that time your program is basically idle, so it is not doing anything. The processor is not executing any instructions, because your program is actually just waiting for some, say, command from the user. So at that time, the CPU is idle, and after, let's say, whenever the event occurs, like let's say if it is waiting for the user command, when the user enters the command, then it will continue its execution. Now the problem is here is that because of this wait time, the performance is reduced, because when the processor was waiting, when the application was waiting and the processor was idle, at that time some other process could have been run on the processor, and that would be like a much better way to utilize the processor. So that would result in a better CPU utilization. So to do so, what we are going to do is like OS supports multi-programming. That means when a process is waiting for, say, some event to happen and it is not actually executing, at that time the operating system can schedule other process on the processor, and then the waiting process is moved to a waiting state, and it can be scheduled again later whenever the event has uh, finished. So after that, here the change in this schedule is that application 1 was running, then it was waiting for an event, so it was moved out, and then application 2 was started on the processor. Then application 3 was scheduled after when application 2 was finished, and then when the application 1 got its event, and it was put into the queue to run, and then it got scheduled again on the processor to run. So basically, if the CPU is idle, then we can switch to another application to improve the CPU utilization. But with the multi-programming, it could lead to starvation. So what is starvation? Starvation means that if an application is running on the processor, then it can run indefinitely, and it may not ever leave the processor, and may not, because of that, no other processes can run or no other applications can run. So like say your application has a infinite loop. So if you start this application, if it starts it running on the processor, then it will run infinitely. So it will just hang the entire system because there is only one processor, and it is the process app 2 here is running forever, and then you will not be able to schedule any other processes on the system. So that's why you need something called preemption. So preemption is the ability of the operating system to stop one process and remove it from the processor and then schedule another process. So even if your process has an infinite loop and it is running continuously, the OS can stop it, preempt it, remove it, and then it can schedule other process. And to improve, to say, avoid starvation and to improve fairness, we can divide the time of the processor time into time slices, or called time quanta. And each application will execute only within one slice. So for example, time slice can be 10 seconds. So each application will be given only 10 seconds to run, irrespective of whether it has finished or not. So it will be run for, like, app 1 will be run only for 10 seconds, then it will be preempted from the OS, by the OS from the processor, and then second app, which is in the second application, which is in the queue, will be scheduled on the processor, and then the third, and then uh, if the next process in the queue is one, then it will be scheduled again. So, so the benefit of this is that first, it avoids starvation. So no one process can completely hook the processor, and every process will get a chance to execute. So because of that, performance will be improved because all the processes will be making some progress with time, right? And also this gives the impression that the applications are running concurrently. So it's not like only one process is running at a time, and it's the user will the system user, to the user it will give the impression that multiple applications are running concurrently. Okay, so it improves the response time, it reduces starvation, and it improves the performance of the system. Now there are, so this we talked about only one resource. So on the first slide we said that OS is the resource manager. Okay, and then first we talk about the processor. So because the processor is also a critical resource actually, and because it is the one which is executing your applications. So first we saw that how the OS manages the this manages the processes, like scheduling on their processor. Okay, how does it schedule the processes on the processor? And next, we have many other shared resources in your system, like printer, keyboard, RAM, disks, files on disk, networks, etc., which are also shared resources, and they also need to be managed by your OS. Okay, so for example, if there are two applications and both of them are trying to print something, then that has to be managed by the OS, like who will be using the printer first and who will be using the second, etc. And similarly, your RAM. So because your what is a process when you're running these applications, the applications are actually brought into the memory, and they're stored in the memory, and then they are executing from the memory, right? So if you're running so many processes concurrently, one after the other, so you have to bring in different processes into the RAM, different. So, okay, so that time, which process will be using which part of the RAM, that is also decided by the operating system. So it has the memory management unit which decides this. Okay, so this was about like how the OS is managing different resources. In particular, we talked about the processor, and then multiprocessors. So So we were talking only in terms of when there is only a single processor and there are multiple applications. But nowadays we do have multi-processors. So our system contains not only one processor, but there are multiple chips, and each chip contains multiple cores. And in fact, each core contains multiple threads. Um, which are unit of execution. So each thread can execute a different process also, and this is called hyper threading. Okay, so this box, outside box, is representing your chip, which has the processor core, and then each processor core will have different threads. So basically, your system is no longer just a uniprocessor, it has multiple processors, and that's why, which allows you to run processes in parallel. Okay, so if let's say if you have these two processors, then application one can be run on processor one, and simultaneously application two can be running on the other processor. Okay, so each processor will be able to execute applications independent of the other. Okay, and then for each of the processor, then again, you, whenever the application finishes its execution, you can schedule the other process. Or you can also apply here the time quanta based scheduling, that on this processor you can specify the time quanta, and application 1 will run only for that time quantum. After that it will be preempted, and then application 2 will be run, and so on, which is like specified here. So like you can have this time slices on each processor, where you will run a process only for its time slice, like say 10 seconds, a fixed time quanta, 10 seconds, and then after that you are going to preempt it, actually not in seconds, but that will be in cycles, like 10 CPU cycles. And so then after that it will be preempted, and then the next process will be scheduled and it will be executing, and then after that, when its slice is also finished, it will be preempted and next can be scheduled, and so on. And they are independent, both of the processes will be independent of each other, and the OS is the manager, which is deciding that your process, on which processor it is going to run. Okay, it's managing, basically it's mapping your processes to these processors and scheduling them. Now, when there are these concurrent executions of multiple processes or parallel executions of the applications, at that time we can have race conditions. So what is a race condition is that, so consider that you have a resource such as say a file, okay, and then you have these two applications, application 2 and application 5, and both of these applications are, let's say, trying to write to the same file. Okay, now since this file is a common resource here, and so if they're going to write it simultaneously, then it can, the values that will be contained in the file will, there is no guarantee on the ordering of these write operations, so they, so you don't know what will be the actual content of the file afterwards. It is possible that what 2 has, the process 2 has written in the file can be overwritten by the application 5. Okay, so this results in this race condition, that you do not know what will be the output because of the concurrent execution of these processes, and therefore you need to synchronize the execution of these applications for such critical resources, like the resources which are being used by multiple processes. And synchronization, you can think of it like a lock. So before you use that resource, you need to take a lock on that resource. So it's like, say, the file is shared resource here. So it's like you will take the lock on the file after. So like the sequence of the steps can be that the process 2 first comes, and let's say it finds that the resource is not being used by any other process. So it will first take the lock on this file. Okay, so it will has, it has taken the lock. Okay, after that it can write in this file. During this time, when 2 has the lock over the file, if application 5 comes and tries to write the file, it will not be able to do so it because it also needs to first take the lock. But the lock is not available, it is already taken by process 2. So when the process 2 will then finish its writing, whenever it finishes its writing, it will basically then unlock the file. Okay, and when it has unlocked the file, at that time process 5 can, when it comes and tries again and it finds that the lock is available, then it will take the lock and then it will access the file and it will be able to write into the file. So, uh, so this is how we synchronize the access of the resources when it is being accessed by multiple processes concurrently, and which leads to race conditions. And this we have already talked about scheduling, that scheduling algorithms, if you've taken a course in OS, you have definitely read about scheduling algorithms in first few lectures of your course. And these are basically the algorithms which are written in your operating systems. So operating system is going to maintain the list of the processes which are ready to execute, like which are in the ready queue. Basically, they are waiting to be allocated to a processor. So then it will look at that queue and it will have a scheduling algorithm, and based on the algorithm, it is going to determine which application should be next scheduled on the processor. Now, for the OS in the scheduling, it needs to be fair. It needs to be fair, which means that only one of the applications should not be, say, always able to run, while the other applications never get a chance to run. Okay, but however, at the same time, it should be able to prioritize some applications. So some applications can be critical, for example, something related to power, or so something like related to, say, your heating system in your, like, cooling system in your processor, etc. So those applications which are very critical applications. So with or like basically it needs to be able to associate a priority to different processes, and when a high priority process comes, then it should be able to preempt the process which is running, which is of lower priority, and schedule the higher priority applications because they are of higher priority. Now, uh, when we talk about OS, another when we said what is the purpose of the OS, so we talked about two. First was hardware abstraction, then there was resource management, and then the third one, which is also very important, is isolation. So isolation, OS provides isolation basically. Now, what does that mean is that the applications which are running in your system, they're isolated from each other, so they cannot access the code or the data. So one application, let's say your team's application, cannot access the code or data stored in the Chrome application. Okay, so the OS provides this isolation. Okay, and for that it uses like the concept of virtual memory management. And why is it needed? It's needed because when multiple applications are executing concurrently, then each application um, can be either from a different user, and sometimes it even they're like, I am the user of the system, they're all my application, but I do not trust the application, like. And in Chrome, let's say I am accessing my banking website, I do not want the, let's say, other processes in the system to be able to get that information, or get my information, any other information, like what I'm searching on Chrome or whatever. I don't want teams to be able to see that, etc. So we need this isolation, which is provided by the operating system, and it also prevents a malfunctioning application from affecting other. So let's say if Teams application has a bug and let's say it crashes, then only Teams will crash. All other applications which are running on my system, they will remain unaffected and my system will not crash. Okay, so the isolation is very important from both like functioning of the system and also from the security perspective. And the OS provides the isolation. But to provide the isolation, the first we need to ensure that the OS itself runs in a protected mode. Okay, what do we mean by that? So your hardware, your processor has different layers or different execution levels basically. Uh, I am sorry, I think I will have to switch to, I may have to switch because my AirPods don't have battery anymore. Can you hear me? Can you just tell me that you're able to hear me in the chat box? Okay, thanks. So, thank you. Then I will continue. Just